Okay, we're back for part 3. Woohoo! Acrylamide synthesis can be reduced by lowering the cooking temperature and time, although this may of course adversely affect the acceptability of the product. For example, you don't want your crisps need to be crispy. The FSA has produced a report on home cooking in acrylamide, which is linked from the image there, and you should read that. And also Food and Drink Europe has produced an acrylamide toolkit. Again, see the link in the image and have a read of that report. The FSA recommends that for home cooking you should aim for a golden yellow or lighter colour when frying, baking, toasting or roasting starchy foods. And some examples there of toast. You should also follow the pack cooking instructions when cooking products like chips or roast potatoes. And also it recommends eating a healthy balanced diet with 5 a day portions of fruit and vegetables. We'll see in a moment why not doing that might be an issue. Okay, this article is based on a study done in 31 primary school canteens in 3 Spanish regions. It's linked in the notes. I think the paper's probably in the Blackboard module as well. Evidence collected included from a frying test, followed by colour measurements and from questionnaires. Acrylamide was measured by a technique called liquid chromatography electrospray ionization tandem mass spectrometry. We don't have one of them. 15.7% of these samples were found to be above the benchmarks established by the relevant EU regulation, which was enacted in 2017. It's EU Regulation 2158. It was found that all samples that were golden or light golden brown had acrylamide concentration below the threshold. We can see that from the 2 graphs there. There's also a good correlation between visual measurements and chemical analysis of acrylamide, supporting the view that colour is a reasonable estimate of acrylamide concentration. Quite wide margins of error. These are box and whisker plots. Don't know what a box and whisker plot is and what it's telling you. You might want to look it up. One method is to remove the asparagine using the hydrolytic enzyme asparaginase. This produces aspartic acid, which can't undergo Maillard reactions. Probably not useful for many foods. Most useful for liquid foods or slurries. So we're talking about reasonably heavily processed food here. See the review link there for a range of applications, of which there are quite a few. It was interesting to see how this is developing. A few years ago you wouldn't have found anything like this many. Okay, Maillard reactions and damage to amino acids. They can also cause something called protein aggregation, which reduces the bioavailability of proteins and so reduces protein quality. We'll have a look at the next slide. We'll talk about that in a second. Lysine is a particular problem since it contains 2 amine groups, so it can undergo more than 1 Maillard reaction per lysine molecule. Lysine is an essential amino acid, that is to say one we cannot synthesize and must obtain from food, so this can significantly affect protein quality. And you might want to do a little bit of background reading on Maillard reactions and lysine and protein quality. It's a reiteration of the previous slide, so we'll move on rapidly. So what is protein aggregation? Basically, it's a random cross-linking between proteins, making them harder to digest. As you know, proteins are highly organized, specifically folded in one arrangement. The cooking causes random cross-links, so it becomes harder for digestive enzymes to get at them. So amino acids may not be released during the digestive process, so become less available. In the developed world, such loss of protein quality is not often considered a problem. However, this article on adolescent diets high in Maillard reaction products suggests that some adolescents may be nutritionally at risk because of their dietary hazards. If they eat a lot of this generic burger and fries, and also the cola, which will contain some Maillard reaction products, they have that 2 or 3 times a day and aren't getting, for example, their 5 a day, they may be, over a long term, increasing their risk of certain negative health outcomes. Here's a food technology example, moving on from health. In this study, the extent of Maillard reactions, aggregation of proteins and textural changes during the storage for high protein bars was investigated. These bars, of course, have quite long shelf lives. It was found that initial Maillard reactions had little impact on hardness, but storage led to dramatic modification of protein with the formation of high molecular weight polymers. That was a quote. that is to say protein aggregates. This led to unacceptable hardness in the product. It was suggested this could be mitigated by the replacement of reducing sugars with ingredients such as sugar alcohols in the product formulation. If you don't know what sugar alcohols are, you might want to look them up and maybe consider what the issues are with sugar alcohols. Before we go any further, let's remember that cooking and food has enormous benefits. We'll look at this later, but for now there's this EUFIC page talks about cooking and the benefits of cooking. Okay, moving on. Maillard reactions and pH. It's complicated in food. Many steps are in the process are influenced by pH, which may change during the course of the cooking process. So very complicated in real food. So people often use models. So here's a model looking at glucose taken from milk protein casein, and as we see, as pH falls, the extent of browning reactions increases. Similarly for fructose, again taken from casein. As pH falls, browning reactions increase. So why? It's to do with the basic chemistry. So the video up the top, I mentioned a bit earlier on. If you click on the link, it will take you to a video showing the process. If you add sodium bicarbonate to frying onions, flavour and colour develop more rapidly than without addition. This is due to the chemistry of the Maillard reaction. So in the middle of these three products here, we've got the three reactants here rather. We've got a amino acid at neutral pH. So you probably did amino acids last year in biochemistry, and you may remember that the pH, the amino acid amine group changes depending on the pH. The nitrogen there has a lone pair, which means that there's a small negative charge. Now the oxygen, the carbon rather, in here has a small positive charge in it. So negative charges attract the positive charges, and that's why the reaction takes place. This is said to be a nucleophilic reaction. If we lower the pH, that is to say, make the environment more acidic, the amino acid loses a hydrogen ion and gains a negative charge. This makes the nucleophilic reaction more likely. So sodium bicarbonate, which lowers pH, promotes Maillard reactions. Conversely, up at the top, if we increase the pH, make the environment more basic, or alkaline if you will, the amino acid nitrogen gains a hydrogen atom and a positive charge. Since the carbon and sugar also has a small positive charge, this makes the Maillard reaction less likely. It will take place but at a slower rate, so the onions will take longer to brown. Chemistry, as I've alluded to a number of times, is more complicated than that, but that's a good general explanation, I think. Here's one for you to research. The influence of Maillard reactions on the colour and flavour of tempura batter. Over to you for that one. Okay, water activity. A reminder about water activity. The equation there is taken from the water activity lecture. The maximum rate of Maillard reactions occurs between the water activity of 0.65 and 0.8. So when people look at reducing Maillard reactions, things like crisps, this is one of the things they're spending a lot of time being interested in. If there's a low AW, that is to say a low water availability, reactants have reduced mobility, so the reactant rate is slower, but then will increase with increasing water activity. Conversely, if the food has a lot of available water, the reactants are diluted and the reaction rate will again fall. So we've got this sweet spot for maximum browning between 0.65 and 0.8, so quite a wide range there. Okay, we'll cap this off by talking about caramelization reactions, which are related, but they aren't the same. Devastating news. Caramels are not the products of caramelization, of which more soon, but of Maillard reactions. If you click on the image, it will take you to a video, which will, and also the link there will take you to some information about caramelization, and the video down here will show you about the caramelization of sugar. So watch both of them. This is the process. It involves successive loss of water to produce very complex proteins, the structure of which are not understood in many cases. Now it goes nothing. It loses water for a while. After about 55 minutes, it forms something called caramelan. Do it for another hour or so, forms caramelen, and for longer it forms caramelin. Note the highlighted letter E to I. It's in alphabetical order. Caramelan, caramelen, then caramelin. As this process develops, we produce small volatile molecules, sugar, which influence the smell and taste. So if you take the classic caramelization, you take some sugar, heat it up in a pan, it's white at the start, just tastes sweet. After a while you get these complex brown compounds, which are complicated aggregates of sugars. Yeah, okay. As I mentioned, the structure of caramels is very complicated, and they've been described as being rubber-like. If you're interested, read this article. Okay, lab reports. Normally we do some lab work on the Maillard reaction. Given the current circumstances, that won't be possible, unfortunately. This will be one of the experiments you will have the opportunity to write up, however. More on the others later. You'll be provided with a sample set of data, and we'll write up the experiment in the normal way. As usual, we'll have workshops on this. Okay, that's all for now on the Maillard reaction.